Hey there, everybody. Um, I'm sure my wife has already broken the news to you. I apologize that I am not able to be there today, Wednesday, or tomorrow, Thursday. I've had some stuff come up with other work obligations that I have that I'm just not able to be there. So I wanted to take some time and make sure that I still gave you guys a lecture that you understood. Um, so we're going to try to go through some things here. I know this isn't super ideal, but I'm going to post this online, and you guys can definitely ask questions from me via email, virtual questions. Um, so I'll kind of give an outline for what we're going to do today. But first, let's just take a minute and pray. Lord, thank you for the opportunity, even with technology, for me to be able to pray with my class here. God, thanks for the victory that you gave the soccer team yesterday and for keeping everybody safe. Lord, for having them all play to your glory. And we pray for upcoming game two that you would just continue to strengthen and uphold and encourage and just uplift the whole team. We love you and praise you. Thank you for this time. In Jesus' name, amen. All right, the plan for today, we're going to review some of the stuff that we talked about with continuity, and then I'm going to take homework questions. I'm going to go through a couple of homework problems that I expect that you probably have questions on. I didn't warn you about this, but the homework, I've decided since I'm not there, I'm going to give you an extra day to do the homework. So the homework's actually not due today, it's due tomorrow. Now I know I'm not going to be there tomorrow either. But that'll give you an extra day to kind of work on some stuff if you need it. You can use that homework to study for the quiz as well. So we'll do a review. We'll do a few homework questions. I'll review and talk about what's going to potentially be on the quiz. And then we'll finish up continuity today. So that's our plan. So just to review, if you remember what we talked about, the concept of a function being continuous, so a function f being continuous at a point x equals a, that actually means, well, conceptually, let's start with conceptually. So first, the idea is that there's no break in the function right at that point. You remember that this type of thing at A is okay right there. But things like this, or, it can get really bad. That's definitely, I would have to pick up my pencil to draw any of these. So conceptually, when we talk about function being continuous, we mean it has no breaks at whatever point we're talking about. The other idea is to take the limit is the same thing as plugging in. Okay, usually plugging in is our first try that we do when we try to evaluate a limit. For functions that are continuous at a particular place, when you try to take the limit, it's the same as plugging the number in. And this gives us kind of our algebraic understanding of limit with our equation. So the limit as x goes to a of the function needs to be the same thing as what happens when you plug the number in. There's really three things going on here. The limit has to exist, the function has to exist at that point, and then the two things need to be equal. Okay? And we talked about what this looks like, ways that this can fail. So the types of discontinuities that we typically see. We have four. You'll remember the first one either looks like this with a hole, or there's, and with no point, or there's a point, but the point is not here, and we call this removable. Okay, that's a removable discontinuity because if I redefine the function here, then suddenly I've removed the discontinuity. The discontinuity is no longer there. We had another one that looked like that, and we called that a jump discontinuity. Okay, and then we had another one, something like that. That would be an infinite discontinuity. And finally, we had something like this. And then we call that an oscillating discontinuity. Okay, those were our four. We reviewed those. And remember, jump, this is not a jump discontinuity. Jump discontinuity means a limit from the left, which we talked about last time too. When I come from the left, I have a limit. When I come from the right, I have a limit. But those, and so those two numbers, there are two numbers that we're approaching, but those two numbers are not the same number. Okay, that's a jump discontinuity. All right. So let's take a couple of examples of some homework questions. I'm guessing. So let me erase this first. I'm just going to make a couple notes on about the homework. So we're in section 1.4. So the first thing I wanted to point out, I don't know if you all have a question on number 8 or not. Let me just note it here. Number 8 says the limit as x goes to 2 from the right of 2 minus x over x squared minus 4. All right. I think the question that may come up here, I don't know if you have this question, but the question that may come up here is, why is it important that I'm coming from the right? And the answer turns out to be it's not important. It doesn't matter if you're coming from the right or not. So you would evaluate this the same way that you would evaluate it if there was no plus there. Okay, you would typically, what would be my first step here? I don't know if I need to go through all of these, but you would factor and cancel, right? So you would probably said plug in. If I plugged in, the top goes to 0 and the bottom goes to 0. That tells me I want to look for one of those techniques that we talked about. And probably the best one would be to factor. So I'm going to factor the bottom as x minus 2 and x plus 2. And then the other thing you have to remember is that this top, 2 minus x, is the negative of x minus 2. So you pull a negative out and cancel and kind of work your magic. You're going to still plug into. Nothing really changes the fact that x is going to 2 from the right. Okay? I'm also guessing that you may have a question either on 15 or on 18. Let's go ahead and look at 15 real quick here. Okay, so I've got a function. And that function is x plus 2 all over 2 if x is less than or equal to 3. And it's 12 minus 2x over 3 if x is bigger than 3. Okay? And they're asking me what's the limit as x goes to 3 from the left of this function. Okay? So the thing you have to identify here, if we do this, is if I'm coming from the left, which function do I use? Okay, the breaking point here is x equals 3, which matches this. So if I'm to the left of x equals 3, I'm going to use which function? This top one right here. So that means when I take this limit, I need to put in there x plus 2 over 2. That's the function that I'm actually using here. All right. And now I just try to plug in 3. So when I take the limit, when x goes to 3, the top goes to 5 and the bottom goes to 2, and that's my answer. Okay? Now if I asked you what's the limit as x goes to 3 from the positive side, then you would use this function instead. Okay, and if I actually plug in 3 there, I get 6 over 3, which is 2. So I could also ask you, is this function continuous at 3? If not, what kind of discontinuity does it have? And it turns out, if you're coming from the left, it's going to 5 halves. If you're coming from the right, it's going to 2. So what kind of discontinuity is that? The jump discontinuity. It doesn't ask, the problem doesn't ask you that, so you don't have to fill that in, but that's a jump discontinuity. Okay. Okay, I think we talked about things like 25, 26. I don't think you'll probably have any questions on that. All we're looking for is, where's the function continuous? What are those intervals? In the places where it's not continuous, describe the type of discontinuity that you have that you're seeing based on the graph. Okay. I'm guessing that maybe there's a question on either 39, 40, or 47. So I'm not going to do 47 because I want you to think about that one. It's kind of like this one that we just did, but let's talk about 40, and then let's talk about, I'm going to look at 45. Number 46 is on your homework for next week. So let's look at number 40 first. Okay. So I've got a function. And it's asking about the continuity. We're going to talk a little bit more about this today. But it says, where is this not continuous? So in other words, if I took the limit versus plugging in, where are those going to be different? Like either I might not be able to plug in, or when I plug in I get a different value. So the thing I told you to look at, this is actually a rational function, right? This is a polynomial over a polynomial. And one of the things that we noticed before that we're going to point out again is that if you have a polynomial over a polynomial, any number in that domain, any number in the domain of that function is actually going to, if you take the limit, it's the same as plugging in. That was one of the rules that we'd actually written down. Taking the limit is the same as plugging in when you're talking about a rational function, a polynomial over a polynomial, when as long as you're in the domain. So in other words, the domain of this function is everywhere except x equals plus or minus 3. So the domain, this is going to be continuous. It's the same, evaluating the limit is the same as plugging in on the intervals from negative infinity to negative 3, negative 3 to 3, and 3 to infinity. This is where it's continuous. Okay, it's not going to be continuous at negative 3 and 3 because that's not even in the domain. So when we talk about our continuity definition, if you don't have the number in the domain, this part of the equation fails. You can't plug the number in, okay? So this is going to be discontinuous at 3 and negative 3. And now what we need to figure out what's actually going on at negative 3 and 3. And I mentioned in class that you can just put this function in your calculator and look at it if you want to. I want to show you, if you don't have a graphing calculator, you don't know what's going on, what's actually happening here, okay? So what I'm going to do is look at the limit as x goes to 3 and the limit as x goes to negative 3 and see what happens, okay? Because that'll be a clue to me as to what's happening here. So let's take a look at the limit as x goes to 3 of this function. Sorry, my pen is starting to be junky here. See if this is better. Yeah, that looks a little better. Okay, if I plug in, I get 0 on the top and 0 on the bottom. I can't do that. But I'm going to factor and cancel. So the top is x minus 3, and the bottom factors as x minus 3 times x plus 3. And then these cancel. So when I let x go to 3, the top goes to 1 and the bottom goes to 6. So in other words, when x goes to 3, from either side, the limit is 1/6. But the function's not defined there. What kind of discontinuity are we looking at? It's a removable discontinuity. So if you take a limit, and the limit exists from both sides, if it was different on each side, we'd have this, which is jump. But the limit, either side, I didn't specify. The limit as we come in is 1/6. It's not defined at the point, so this has to be a removable discontinuity. Okay? So that has to be a removable discontinuity. Hope that makes sense. Now you could see it from you could probably see it from a graph. The graph won't have the hole there, so you have to be careful. Okay, so then at -3, let's look at what happens when x goes to -3. Okay, when x goes to -3, the top is actually becoming -6, and the bottom is actually going to 0. Now I mentioned we're going to be doing this case in the next section. This is one of the reasons I'm not too thrilled about the order of the sections here. You kind of needed to see this before. But basically what's going on here is the top is going to getting close to -6, and the bottom is getting smaller and smaller and smaller. And I don't know if you've thought about the fact that when you divide by a really, really, really small number, the resulting thing is really, really, really big. So when you have something like this where the top isn't going to 0 and the bottom is, this is actually an infinite discontinuity. And if you were to graph the function, you would see that. Okay? We're going to study this a little bit more in depth in section 1.5. So we have a removable discontinuity in one case and an infinite discontinuity in the other case. I think this function actually looks like, if I've got it right, it's got a removable discontinuity right there. Yep. Okay, it looks something like that. Okay. So hopefully, I would say any questions, but you can't ask them, so I apologize for that. So let's look at, the last one I want to look at is 45. Uh, 45 was not on the homework, so don't freak out. 47 was on the homework, but 45 is really similar. Okay, so for 45, my function is x if x is less than or equal to 1, and x squared if x is bigger than 1. Now, these are simple enough that we could actually graph these. I want us to be able to get the information that we need without graphing. So we're going to try to do it a different way. Later on, I can graph it and we can see what's going on here. So it says, where is this continuous? Well, I want you to think about the fact, I told you I wasn't going to graph it, and I'm not going to quite yet. But if we're to the left, this is the function x, and the function x is a polynomial. And for polynomials, if you plug in versus take the limit, it's the same thing. So this function is going to be continuous everywhere over here. There's going to be no breaks because this is a polynomial. And then because x squared is a polynomial, the function is actually going to be continuous on this region too. So really the issue that we have to deal with, I think I gave an example last time with this, where we had a kind of an x squared and something like this. The question is, do these meet up, or do they kind of jerk like this? They are, so in other words, are we going to get a jump discontinuity, or are these actually going to match up? Okay. So we're continuous everywhere outside of 1. So really what we need to do is examine what's going on at 1. And because the function's different on the left and right sides, you can probably guess what I'm going to do here. I'm going to take a limit from the left, a limit from the right, and see if they match up. Okay, so let's first start with a limit from the left side. So if I come from the left, which function am I using? That's the function right here, x. And when x goes to 1, x goes to 1. Right? Okay, so when we come from the left, the function actually goes to 1, and we kind of know it actually looks, it's the function x, so it should look like this. And there's actually a filled in hole there because this is less than or equal to. Okay, let's come from the right side now. And if I come from the right side, I want to use the function x squared instead. But when x goes to 1, x squared also goes to 1. So what's happening there is that as I come from the right side, that's also going into 1. So does this have an overall limit? Yeah, the limit's 1. And if you think about when I plug in 1, f of 1, that's also 1. So all of these things agree, and that means this function's continuous right at that point too. So this function is actually continuous at every single point on the real line. Okay, so what you're going to need to do on 47 is something similar to that. Okay, hopefully that answers most of your homework questions. If you want to turn in your homework now, that's fine. You can give it to Mrs. Myers. If you want to wait and turn it in tomorrow, use it to study for the quiz, that's fine too. So I said the word quiz, so don't freak out. So just to kind of let you know, really the topics that we've talked about since we took our last quiz are evaluating limits algebraically, and then continuity. Okay. So really the types of things that you would see on the quiz, number 1, I might give you a limit and I'd say evaluate this, and the first thing you should always try to do is plug in. But you may run into issues. For instance, if you have a fraction and the top and bottom goes to 0, then there's 4 things you're supposed to try, right? Factoring, factor cancel. If you see a square root, you do the conjugate. If you see a fraction in a fraction, you do common denominator. And then in some other way, you try to simplify. Okay? And then, if all else fails, you've got the squeeze theorem. I'm probably not going to throw the squeeze theorem at you tomorrow, so if I did, it would be an example that you've already seen. So hopefully you would expect in this portion, I'm probably just going to give you several limits and say, evaluate these limits, try plugging in. If that doesn't work, use some of the other tools that you've already developed. Okay. For continuity, you need to know how to check if a function, well, you need to know the definition that the limit coming into the point is the same as plugging in. Okay, so that equation is important. you need to know from a graphical standpoint, where is a function continuous and where is it not? You should be able to look at a graph and say, oh, it's continuous here, it's not continuous there. And you should be able to identify the different kinds of discontinuities. Okay, so the different ways that a function can be discontinuous, those 4 ways that I just reviewed. And then if I give you a formula, so kind of algebraically, if I give you f of x equals some formula, again, you should be able to look at that formula and say, that's a polynomial, so it's continuous everywhere, or that's a polynomial over a polynomial, so the only places where it might be discontinuous are the places where the bottom is 0. Let me check those. I check those by looking at limits. Okay, does that make sense? So that's the type of stuff that you should expect to see on the quiz tomorrow. Okay. All right. So the things that the rest of the things that we need to do today to finish up the section on continuity, I want to talk about one of the things that gets confusing in this section. When we talk about continuity, there's actually a lot of different definitions for continuity, and I'll explain what I mean by that. So we have a definition, a function being continuous at a point. Okay, so a function is continuous at a point if this equation right here happens, right? The limit as you come into that point is the same as what happens right at that point, okay? Now what starts to get confusing is that we talk about continuity in other situations too. So let me give you an example of what I mean. So the book turns around and then they say, okay, I'm going to give you a definition of what it means for a function to be continuous on an open interval. Okay, you remember open interval, don't freak out. Open interval means just this interval from A to B, not including the 2 endpoints. So I might say, for instance, I've got a function that's continuous on the interval from 0 to 5, not including 0 or 5. Okay, what the book means by this, we already know what it means to be continuous at a point. What it means to be continuous on an open interval, this means f is continuous at every point in the open interval. Okay? So let me just illustrate what I mean. So let's suppose I've got a function that's continuous on the interval from 1 to 4. Okay, I don't know what that function looks like, but I know if I were graphing from 1 to 4, I'm not saying what's happening at 1 or 4. I'm just saying between 1 and 4 it's continuous. Okay, what that means, the definition of that is that if you pick any point in here, like 1.7, I don't know, I'm just picking a random point, the function's continuous there. If you pick another point, 3.5, the function's continuous there. It's continuous at every point in between 1 and 4. That's all that means. Okay? So we've got a definition for what it means to be continuous at a point. Then we've got continuous on an open interval. Okay? So an example, maybe to give you an example, because this might seem, if I had the function x squared on the interval from 0 to 4, okay, from 0 to 4, that function is continuous, and all that means is if you pick any point in here, that the function is continuous right there. In other words, right at that point, if I take a limit versus I actually plug in, I'm going to get the same thing. Okay? So it's not, it sounds complicated, it's not really complicated. So continuous on an open interval just means continuous at every one of the points in that interval. Okay, then the book turns around and they say, okay, what does it mean for a function to be continuous everywhere? Or continuous on the real line? Anybody have a guess as to what that means? Okay. Function being continuous everywhere. What that means is that everywhere, it's kind of like continuous on an open interval. Everywhere, if you pick any point, the function is continuous at that point. Okay, so this means f is continuous at every point. Okay, so we don't just have an open interval, we have the entire real line. So you'll see terminology where it says f is continuous everywhere. Okay, so an example of a function that's continuous everywhere, f of x equals x squared, that's continuous everywhere. Okay. Yeah. Okay. All right. So now we'll throw in kind of a little bit weirder example. So we've got an idea of what it means for f to be continuous on an open interval. What would it mean for f to be continuous on a closed interval? Okay, what if we include the two endpoints? This is where things get a little weird. So let's take kind of our classic example of a weird, something weird that happens on a closed interval. Let's take the function square root of x on the interval from 0 to 4. Let's just say. Okay? Okay, and I'm including 0 and I'm including 4. Now, again, you should be able to draw the function square root. It looks like that. So here's what I want to ask. If I pick any point between 0 and 4, clearly, like, I guess this looks about like 2.5. Clearly the function's continuous based on the graph. It's continuous there. If I take a limit versus plugging in, it's the same thing. But something goes wrong at the endpoints. What goes wrong at the endpoints? Is this function continuous at 0 or continuous at 4? This is where we have to go back to that idea of, our definition of continuity is, let me write it up here again. The limit is the same thing as plugging in. What goes wrong in the square root function, particularly at 0? There's a limit from the right, but there's not a limit from the left. So for the square root function, at 0, there is no limit right here, which is weird. So the function's actually not continuous there because this left side doesn't exist, right? I mean, it's kind of dumb, but according to our definitions, because we can't take a limit from the left, it's not going to work there. But it is continuous from the right. I mean, there is a limit from the right, and it matches up with what would happen if you plugged in, right? That part seems to work nicely. So what we're going to do is we're going to sort of, because this issue with closed intervals, we have an issue at the endpoints, we need to kind of give another definition. We need to talk about what it means for a function to be continuous from the right or continuous from the left at a point. Okay, continuous means if you take a limit from both sides, it matches up to what happens when you plug in. Because we can't take a limit from both sides, we have to talk about coming in from one side only or coming in from the other side only. So we're going to give kind of pause on this just for a second. And we're going to say f is continuous from the right at x equals a if, okay, we're going to use the same equation. Taking the limit is the same as plugging in, but we're only going to come from the right side. Okay, so the only change, if we only want to be continuous from the right side, is that we're coming in from the right side, and that needs to be the same thing as plugging in. Okay? So as an example here, the square root function is continuous from the right at 0, but it's not continuous at 0. Does that make sense? It's continuous from the right because I can take a limit from the right side, but it's not continuous overall at 0 because I can't come from the left. Again, you may be like, this is dumb, why are we doing this? But that's just that's a product of the definition that we have. Okay? Similarly, if I was coming from the left side and there was nothing on the right side, this function would not be continuous here either, and that's kind of silly. So we're also going to define that a function is continuous from the left at a point if we're only using the limit from the left, and that is what happens when we plug in, okay? So the only change here when we talk about left is that we're coming from the left side, okay? So let me give an example here before we go back to okay, if I had a jump discontinuity like this, notice that when I come from the left side, this is at 3, when I come from the left side, that's the same thing as plugging in. So this function is continuous from the left at 3. But this function is not continuous from the right at 3 because if I take my limit from the right side versus plugging in, those are totally different values. Okay, does that make sense? So you can be continuous from one side and not the other. Kind of one example is square root of x. Another example is if you have a jump discontinuity and one of those holes is filled in. Okay? So the book throws in these definitions of a function being continuous from the left at a point and a function being continuous from the right at a point. And so now, if I want to talk about a function being continuous on a closed interval, I just erased what I wanted to find. So if I want to talk about a function being continuous on a closed interval, let's go back to our example. Square root of x on the interval from 0 to 4. What this should mean, if I want a function to be continuous on a closed interval, that should mean that the function is continuous on the open interval. So it's continuous everywhere in here. And then what should happen at the two endpoints? If I'm at the left endpoint, I don't know what's happening on the left side because I'm not assuming anything about what this function is doing on the left side. So if I want to be continuous right at this point, I can only talk about being continuous from the right there. So the function is continuous from the right at 0. And then likewise over here, if I'm on the right endpoint, and I want to talk about the function being continuous overall here, I can only talk about coming in from the left side. Okay, so its function is continuous from the left at 4. Okay, so in general, if I tell you that I have a continuous function on a closed interval, what that means is that it's continuous everywhere between the two endpoints, so it's continuous on the open interval. And then you minimally know that it's continuous from the right at the left endpoint, and it's continuous from the left at the right endpoint. Okay? Okay, so that's what it means to be continuous on a closed interval. Continuous on an open interval, it's just every point in between. It's continuous. But when I include the two endpoints, I don't know what's happening out here necessarily. So I have to talk about being continuous from the right here at the left endpoint and being continuous from the left here at the right endpoint. Okay? So that's what it means for a function to be continuous on a closed interval. Okay. You're probably like, great, that's lots of nice continuity definitions. We have one more. What does it mean for, and this one is hopefully shouldn't be crazy. What does it mean for a function to be continuous on its domain? Okay. Well, all that means is that whatever the domain is, if it's open intervals, it's continuous on that open interval. If it's closed intervals, it's continuous over here, and then on the endpoint, it's continuous from the direction that we want. So, kind of as an example, for the function, let's say the function 1 over x squared. Okay, what's the domain? The domain is negative infinity to 0, and then 0 to infinity. It's continuous over here because it's continuous at each one of these points. And it's continuous over here because it's continuous at each one of these points. So this function is continuous on its domain. Okay. Similarly, if I go, let's do square root. The domain here is 0 and onward. So if I ask, is this function continuous on its domain? We've got a closed interval here. So every point over here it's continuous at, we know that. And then when we're looking at the left endpoint, we don't, and we're talking about continuity, we're not talking about coming from the left and right sides. We just care about what happens when I come in from the right. And if I come in from the right, that's the same as plugging in. So it works at that endpoint too. So this is also continuous on its domain. And in fact, all of those functions that we had listed all of those functions that we'd listed kind of in class before, where we were talking about taking limits. So if you take a limit, is that the same thing as plugging in? That means continuity, right? Anything like, remember we had this list of constants, x to the n or nth root of x, polynomials, rational functions, which are polynomials over polynomials, trig functions. These functions are all continuous on their domains. Those are all nice functions as long as you can plug a number in. They're going to be continuous. Taking the limit is the same as plugging in a number. Okay? And actually, any combination, any combo of these functions is also continuous. So when you take continuous functions and you combine them, if I add them, subtract them, multiply them, divide them, as long as the bottom doesn't go to 0, right? We have to be careful of domains here. Or compose them. If I combine continuous functions together, I get continuous functions, okay? Which is nice. We would really prefer for that to happen. So in other words, if I have, like if I take a trig function and a rational function, I don't know, let's do a trig function, let's do something simple. A trig function of polynomial. If I say sine of x squared plus 3x plus 2 is my function, and I say, where is this continuous? This function right here is continuous in its domain because it's a polynomial, so it's continuous everywhere. Continuous everywhere, the whole real line. This function sine, the outer function, you kind of know what that looks like, right? That's also continuous everywhere. It's continuous on its domain, which means the domain is everywhere. So that's continuous everywhere. So when I compose them, this gives me a function that's continuous everywhere. Okay. My computer just logged out. Okay. So I think this is, so all this to say that when you see the word continuous in the book, you have to be really careful because typically the book is saying continuous with some sort of qualifier. So like continuous at a point, continuous on an interval, open interval or closed interval, continuous everywhere, continuous at a point from the left or continuous at a point from the right. So when you see the word continuous in this section, you have to be careful that you don't just say the function's continuous and then don't read the rest of it. The rest of it's important. There are different ways that we can be talking about continuity at a point from one side versus the other, or on an interval, or on the whole real line, or on the domain of a function. All of those are kind of slightly different concepts, right? All right, so let's take a 5-minute break here, and then we are going to come back, and there's one property of continuous functions. We'll look at a couple examples of continuous and non-continuous functions, and then there's one property of continuous functions that is one of the things that we're working up to in this section. So take 5 minutes. You can pause this video, and we'll come back and finish up the section. All right, we are back. Okay, now before we do this last application, one thing that I just want to ask, what real world functions are continuous versus discontinuous? Okay, so in other words, I want you to think about the type of discontinuities that you've seen before. What functions, what real world examples of things do I know where things have to be continuous with no breaks versus things can go along and then suddenly change like that? So let me give you a couple examples. Most of the examples that you think of probably fall in this category. So for instance, if you think of let me give you a function. Let's say take the function of the temperature in your body over time. So the temperature in your body goes up, goes down. It may go up during the day. It may go down at night. It may go up if you're taking a hike and you're out sweaty. Maybe it's hot outside, or if you go and shovel the driveway, your temperature of your body may get lower. Is it possible for your body temperature to be here and then all of a sudden go, or for it to be here and go? No. Okay, your body temperature, it may go up quickly, but it's still going to be in some sort of continuous fashion. Okay. Another example would be if you measured somebody's height over time. Generally, the way people grow and shrink, they start out small, and then they're going to gradually get bigger. They're probably not going to go like this, and then all of a sudden, immediately, they're that much higher. Now, I guess technically, if you measured somebody's height over time, and they went along, and then all of a sudden, one day somebody chopped their legs off, all of a sudden, they would go from here down to a height much, much lower. I guess it's kind of gruesome. An example of a couple of real world situations where you would actually have discontinuities would be something like altitude. So if you were walking along and you were measuring your altitude, and then you came to a cliff, if you stepped off the cliff, the altitude that the ground is at is suddenly down here versus here. So altitude of the ground is an example of a discontinuous function. So based on where your position is, you're suddenly going to get a discontinuity there. It's going to be a jump discontinuity. Another example is the amount of electricity or the amount of light running through a particular room. So you start with a room, if the lights are off, you have no light, you have no electricity running through the lights. When you flick the switch, electricity actually instantly, it doesn't kind of come on like this, it just goes boom, right? So suddenly the amount of light went from here up to here, and you get a jump discontinuity. So there are real world situations where you have continuity versus discontinuity type situations. Okay? So you might think about, what are some other examples? There's a lot of examples of ways that you have continuous types of things happening, but what gets interesting is when you think about ways that you can have discontinuous types of things happening. Okay. The last thing we're going to do in this section is talk about a very special property of continuous functions that it's important, so it's not, Zach loves the word lemma, it's not a lemma, it's actually a theorem. This is called the intermediate value theorem. The intermediate value theorem. And it comes up enough in math that we actually give it some initials. We call it IVT. Okay, the intermediate value theorem. All right, so I'll explain the concept of the theorem before I sort of write out the theorem. I want you to think about, if I had a function, and let's say at 1, the function has the value of 5. So here f of 1 is 5. And then at 4, 2, 3, it has a value of 2. Okay. So at 1, it's 5, and at 4, it's 2. And what if I told you that this function is continuous on that closed interval? So it's continuous everywhere in between, and it matches up correctly at the two endpoints. So is it possible for this function to miss the y value 4 in between? So in other words, can I connect these 2 points in a way that still gives me a function and is continuous, but doesn't hit this line y equals 4? The answer should probably be no. If it's continuous, that means no breaks. Now, if we don't have discontinuity, we could have something like this happen, right? I could go up, and I could have a jump discontinuity, and this function doesn't hit the y value of 4 at all. But if I'm not allowed to do that, and you try to connect these two sides, at some point, in order to connect the two sides, you're forced to come down. You're forced to come down and hit that, come down to this other point, and then at that special point, you hit the y value of 4. So what you should see here is that, in fact, this function, because it's continuous, it hits every single value between, y value between 5 and 2. At some point, it's 4. At some other point, it's 4.5. So it hits every single one of these values. It may hit other values too, but it hits every value in between. So the nice property of continuous functions is if they hit two different y values, and it's continuous, it has to hit every value in between. And that's why it's called the intermediate value theorem. Okay? So the statement of the theorem is that if f is a continuous function on the closed interval from a to b, and so let me draw this picture in general. So I've got the interval from a to b, and I've got a continuous function, and let's call this place f of a, and this place f of b. I don't know where they are, but I'm just kind of making a picture. Okay? And then if I pick another value, another y value, let's call this L. Okay? And if L is a number between f of a and f of b, so if we pick another y value between where the function hits at a and where the function hits at b, then there is an x value, so there's a number c, there is at least one number c where the function hits that value L at c. Okay? Let me give you a second to write this down. Okay, so it's saying, if I've got a closed interval from a to b, here's f of a and here's f of b. If I pick any other y value between these two f of a and f of b values, there's some place where the function crosses that y value. So in other words, there's a place, which I'm calling c, where when you plug in c, you get L. Now there could be more than one place. The function could go like that. I could have several places where I hit that y value. But I have to have at least one place. It can't just skip over that value. So again, maybe in practical real world terms, if I had somebody who was 5 feet tall when they were 10 years old, and they were 6 feet tall at 16 years old, so 5 foot, 6 foot, is there an age where they were 5 foot 10? Yeah, there has to be. It has to cross. Okay, you can't be 5 feet and then suddenly jump up to 6 feet. You can't miss anything. It has to be continuous in between. Okay? So this is saying if you're down here at point A and you're up here at point B and I pick some value in between, there has to be some place where the function hits that value. Okay, that is called the intermediate value theorem. And we use this theorem in a lot of different contexts. I want to give you just 2 or 3 examples. And these are the kinds of examples that you'll see in the book. This is sort of around 67, sorry, 66, 76, 77, or problem 80 in your book. Okay, so let's take an example here. Okay, so for example, show there is a place where x squared plus 3x minus 1 equals 0. Show that there's some place where this function equals 0. Okay? A place where a function equals 0 is actually, there's a lot of important applications of this in math. We call a place where a function equals 0, we call that a 0 of the function. So you'll see sometimes questions will ask, show that this function has a 0. What that means is a place where you can plug in and get the function to equal 0. Okay? So the way we're gonna do this with the intermediate value theorem is that let's call our function f so we can refer to it in some way. So this is going to be our function right here. I want to know that this function has a place. I don't know what the function looks like right now because in order to do something, I'd have to complete the square and stuff. I want to show that this function crosses y equals 0 somewhere. The way I'm going to do that is I'm going to find a place first where the function is below 0. And then I'm going to find a place where the function's above 0. And if this function's continuous, it has to cross, right, by the intermediate value theorem. That's what the intermediate value theorem says. So if I want to find a place where a function equals 0, I have to find a place where it's below 0 and a place where it's above 0. And then some place in between it has to cross. Okay, so what I'm going to do this is just start trying random numbers. Okay, so let's try, for instance, if I plug in 0 in this function, I would get 0 plus 0 plus negative 1. So when I plug in 0, I get negative 1. Okay. If I plug in, let's pick another number. I'm just randomly going to, not random, but I'm just going to pick another number. So I'm going to pick 2. If I plug in 2, I get 4 plus 6 is 10, minus 1 is 9. So at 2, this function is way up here at 9. Okay, so it's below 0 here, and it's above 0 here. Now, in order to conclude that the function has to cross, there's one more thing I need to notice in order to use the intermediate value theorem. I need to notice that the function is continuous on this interval from 0 to 2. Now, the reason this function is continuous is that it's a polynomial, right? So it's a polynomial. So it's continuous on that interval. It's actually continuous everywhere. So because of these 3 points, it's below 0 here and above 0 at 2. And then it's continuous in between then what I write is by the intermediate value theorem, we know there is a place where the function equals 0. We don't know where it is beyond that it's somewhere between 0 and 2. We don't have any more information than that. But the intermediate value theorem guarantees us that there's a place where this function actually equals 0. If we wanted to try to get better information, what we could do is we could try plugging in a different number. Like if I plug in 1, I get 1 plus 4, minus 1, I get 3. So at 1, it's 3. So you can kind of tell not only is the place where it crosses between 0 and 2, it's actually between 0 and 1. And so then I could try plugging in other numbers, like maybe a half, and seeing where that is and try to hone in on that. That's actually there's a technique for doing that where you find places where the function equals 0 by slowly kind of honing in on those values. But the intermediate value theorem guarantees us that there's a place where this function crosses. Okay, if it's continuous, it's below and then above later, and it's continuous, it has to cross, it can't jump, because that would not be continuous anymore. Does that make sense? Hopefully. Okay. Let's take another example here. Show that there is a place where the function x cubed minus 2 equals 0. Okay? So I'm going to do this the same way that I did the one that I just did. So in order to talk about a function, let's define it. So let's let f of x be that left function. X cubed minus 2. Okay, I don't know, I kind of do know what this function looks like. It's actually, remember, it's x cubed, and then what am I doing? Going up or down? Going down 2. So I've picked kind of an easy function here, but there's a reason I picked this function. Okay, let's find a place first. So in order to know this function equals 0 somewhere, let's first find a place where it's below 0, and so I'm going to plug, 0 is always a great number to plug in. So if I plug in 0, I'm going to get 0 minus 2 is negative 2. And so that means the function at 0 is down here. Let's plug in 1. Well, when I plug in 1, I get 1 minus 2 is negative 1. It's still negative. I haven't crossed yet. Let's plug in 2. If I plug in 2, I get 8 minus 2. That's 6. So then we're way up here. So what you can tell now is at 1, I'm below 0, and at 2, I'm way above 0. In order to conclude that I cross, there's one more thing I need to note. That this function is continuous on that interval from 1 to 2. And the reason it's continuous is it's a polynomial. Polynomials are continuous everywhere in their domain, which is all real numbers. So that allows me to conclude that by the intermediate value theorem, there is a place where this function equals 0. Okay? It has to cross somewhere in between. There could be more than one place. Technically, it could go like that. This function actually doesn't do that, but it could do that. Okay? Now let me point out something here that's actually the reason I used this example. So if this function equals 0 somewhere, let me bring the 2 to the other side. What this is saying is that there's a place where when there's some number that when you cube it, you get 2. Now you would kind of intuitively say, of course there's a number that when you cube it, you get 2. It's called the cube root of 2. When you cube the cube root of 2, you get 2. But what this theorem actually, what you just proved, is that this number actually exists. There really is a number that when you cube it, you get 2. You might think that, if I take, in my calculator, I put in 2 and then take the cube root, the calculator spits out some number like 1 point, blah, 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 like 1.3, 1.2. But if you take that number and cube it, you don't exactly get 2. You get something close to 2. So the question is there really a number that when you cube it, you get exactly 2? And what you've proven here with in the intermediate value theorem is yes, there actually is a number called the cube root of 2 that when you cube it, it's not just close to 2, it is exactly 2. Does that make sense? So the intermediate value theorem actually has some really interesting applications. There's one application of the intermediate value theorem that this is not I wouldn't throw this on an exam, but it actually, this is kind of our last example for today. Let's suppose that you were driving from Grand Rapids to Detroit. Okay? So let's suppose that you're driving from Grand Rapids to Detroit. Let's say you're going to do it tomorrow. So you're going to start on Thursday. You go from Grand Rapids to Detroit. You start in Grand Rapids at 8 a.m. And you take a particular route, and you arrive in Detroit. I don't know how far away Detroit is, about 3 hours. I'm just guessing here. So let's say you arrive in Detroit at 11 a.m. Okay? And you go that direction. So that's Thursday. Okay. Then on Friday morning at 8 a.m., you start back from Detroit. So at 8 a.m. on Friday, you start back from Detroit and you drive back toward Grand Rapids and arrive in Grand Rapids at 11 a.m. Okay, you get the scenario? So we start Thursday morning at 8 a.m. in Grand Rapids. We take a particular route and we get to Detroit at 11 a.m. The next morning on Friday, we start at 8 a.m. We take the same route back, and we get to Grand Rapids at 11 a.m. Prove that at some point in this route, you were there at the exact same time on Thursday and Friday. Prove that somewhere on this route you were, so like for instance at 9:25, you were right here at the same time. Doesn't matter if there was traffic one day and not traffic the next. None of that actually matters. What we're going to do is we're going to prove this using the intermediate value theorem. It's actually going to be very, it's going to seem super theoretical, but it actually makes it very simple. Okay, so we're going to let, okay, so we're going to let, let's see, let's let f of t be our distance from Grand Rapids on Thursday. So we have a function that over time we get farther from Grand Rapids. So that function might look something like, so at time 0, let's say time 0 is 8 a.m. Okay, let's at 8 a.m. We are right in Grand Rapids, so our distance is 0, and then at 11 a.m. we are in Detroit, which is some other place. Okay, so we have some graph that over time we made some progress in getting away from Grand Rapids. Okay, then let's let some other function g of t be our distance from Grand Rapids on Friday. Okay, that g of t function, what's going to happen is it's going to start in Detroit, so you're far away from Grand Rapids. Right? This is Grand Rapids. This is Detroit. You're far away from Grand Rapids, and then at 11 a.m. you're in Grand Rapids. Now you can already kind of see that in the way I've drawn this, these two functions have to cross because distance functions are continuous, but we need to make this a little bit more, rigorous. So what we're going to do is we're going to let h of t be the distance between these two functions. Okay, it's the difference between them. F of t minus g of t. So what I want you to notice is that at 8 a.m., so in other words, if I'm plugging 8 into both of these functions, the first function I was in Grand Rapids, so my distance to Grand Rapids is 0. And the second function, however far Detroit is from Grand Rapids, you know, this is 115 miles or something like that. So when I plug in 8 in this function, I actually get a negative number. If I plug in 11, so where am I at 11 on Thursday minus where am I at on Friday, here I get a positive number. And each of these functions is continuous because it's a distance function, so this h function is continuous. So by the intermediate value theorem, if at 8 o'clock it's a negative number, and at 11 o'clock it's a positive number, at some point it has to cross 0. So there has to be some place where this function is 0. In other words, the difference between my routes is 0, and that means that there's a place where at the exact same time you're in the exact same position. Okay, this doesn't tell me where it is, but somewhere in between, no matter what happened with traffic, no matter what, if we have this set up, someplace in between, there was a time and a place where we were in the exact same time and the exact same place on 2 different days. Interesting. All right, I think that's enough for today. So we may be a little early. If we're a little early, you can kind of finish up on the homework, start studying a little bit for that quiz. Remember, the quiz is not, the homework's not due until tomorrow. We'll go ahead and pass out, if Mrs. Myers hasn't done this already, we'll pass out a homework sheet for next week. So that has the homework. Next week we've got section 1.4, a little bit more, and then this next section, section 1.5. Then tomorrow we've got our quiz, and we'll be looking at one last type of limits, infinite limits, and it's not going to be too intense, so we should be good there. All right. Have an awesome day, and I will see you at least virtually tomorrow.